Okay, this lesson is on optimization. We're learning to use calculus to solve a problem that involves making an equation and then finding the maximum or minimum value over an interval. Okay, these are usually the most challenging word problems you learn in grade 12. We would usually spend 2 days and do a bunch of different types, but because of this year, we're going to focus on just a few. There's an algorithm for an optimization problem. Step 1, draw and label a diagram and make a word equation about what it is you're trying to optimize. Step 2, make an equation that represents the quantity you're trying to maximize or minimize. Your equation might be a function of more than one variable here. And then in step 3, you're going to use mathematics to rewrite the equation in terms of one variable only, usually using information given in the question. Step 4, determine the domain of the function and make sure you choose a closed interval so that you can test the endpoints. Okay? And this will likely be one of the most challenging parts of the question. It relies on physical constraints. Sometimes you're given information from the problem, and also your ability to just visualize the possibilities and what interval would make sense. And then the 5th step is to apply the extreme values algorithm from what we did in max-min problems. Okay, so you test the spots where the tangent is horizontal, possible peaks or valleys, and you test the endpoints and come up with your maximum or minimum over that interval. So here's our first example. A farmer has 800 meters of fencing and wishes to enclose a rectangular field. One side of the field is against a road that's already fenced, so it doesn't need fencing. What dimensions should the farmer use in order to maximize area? And we're going to do this using calculus. So here's my roadway, and here's my fencing. Okay, and I'm going to call this dimension x and this dimension y. All right, and what is it we're trying to maximize? We want to find the maximum area. Okay, and we can see that. So we've drawn and labeled our diagram, make a word equation. We don't really have to. In this case, we're maximizing area. Make an equation that represents the quantity that might involve more than one variable. So the area of this that I've just drawn is x times y. But now we want to make it as just a function of x. So how are we going to write y then? So it's something to do with x. Well, we have this 800 meters of fencing, and we know that 2x's plus that y has to equal the 800 meters of fencing that we have. So another way to look at that is that y is going to be 800 minus 2x. So now we can come back here, instead of just having area, we can have area as a function of x is x times y, which we said was 800 minus 2x. And we also want to make it easy to find the derivative, so I'm going to distribute there. So there it is as a function of x, the area. But now we want to state our domain. So x has to belong to a closed interval. So here's where we imagine our possibilities. So if we have 800 meters of fencing, and here's x, we could have x be 0. It wouldn't make much sense, but if x was 0, then the fence would just be right up against the roadway. So you have 800 meter long fence right up against the road. Definitely is not going to be your maximum area, but that's an extreme possibility, right? The other option is we can have our x be as large as possible. So basically perpendicular to the road, my two equal lengths of fencing right side by side. Again, you have no area enclosed, but because you need the two fences here and they have to add up to 800 meters of fencing, they could each be 400 meters long. So they're within 0 to 400 has to be your value of x that's going to give you a maximum area. Okay, so Now we apply the extreme values algorithm. So we want to find a prime at x. So derivative is 800 minus 4x. Set it equal to 0 and solve for x. And we get x is equal to 200. So that's where we have a peak or valley. So test peak or valley. So we're going to find a at 200. So a at 200, I think I'm going to choose this form to work with. So 800 times 200 minus 2 times 200 squared. So 800 times 200 minus 2 times 200 squared is 80,000. So 80,000 meters squared we got for our area, and now we're going to test the endpoints, which are 0 and 400. So a at 0 is 0 square meters. And a at 400 should also be, because of 0, because it would be the two fences facing up to each other. But we'll show it. And if you type that into your calculator, 800 times 400 minus 2 times 400 squared, you do get 0. So that means our maximum, this is our maximum area here. And then also with these questions, you have to make sure you actually answer the question they ask. So what dimensions should the farmer use in order to maximize area? So they don't ask you for the maximum area, they say what dimension should you use? So back to our picture here, we know that x should be 200, so we know these each should be 200 meters. And if there's 800 meters of fencing, that would mean that this should be 400 meters of fencing. And then you want to make a nice therefore statement. So therefore, to maximize area, the portion of fence parallel to the road should be, so facing the same direction as the road, should be 400 meters, and the other dimension should be 200 meters. So that says we want a 400 by 200 meter fenced area, rectangular area, where the portion that's parallel to the road is 400 meters. Okay, make sure again that you've answered the question they asked, shown your proper communication. All right, so we're going to move on to a little more complicated one. I'm going to show you 3 types, so this is kind of the easiest type, then we'll do like a medium, and then our most challenging one. So a supermarket is designed to have a rectangular floor. So already we know it's rectangular. And we know its area is 3,750 square meters with 3 walls made of cement blocks. So 3 walls made of cement blocks and 1 wall made of glass. In order to conform to building code, the length of the glass wall must not exceed 60 meters, but not be less than 30 meters. That is giving us our interval, which I always love when optimization questions give you the interval. The cost per linear meter of the glass wall is twice the cost of the cement wall. Find the dimensions that will minimize the cost of construction. So let's draw a rectangle to represent our supermarket. And because the cement is cheaper than the glass, probably we're going to end up with the glass wall being shorter. So this is going to be cement. This is probably the front of the store or the supermarket. Glass at the front, cement again, and cement again. And also we're going to have them, I'm going to have my glass be X, and then this has also got a length of X, and then the other two walls have a length of Y. And we're finding the dimensions that will minimize the cost of construction. Okay? So when we start off our word equation, and I probably would do one for this, I'd want to say cost is going to be the cost of cement walls plus cost of glass walls. So if I'm following my algorithm, I've drawn a picture, and my cost, I've kind of written it out in words. The cost that I want to minimize here is going to be made up of the cost of the cement walls plus the cost of the glass walls. So I'm going to change from cost to just C for now, for cost. Cement walls, it says, so a glass wall is twice the cost of a cement wall. So I'm going to, because they don't give me specific ones, as long as I make glass twice as expensive as cement, then I should be okay. So I'm going to have my cement walls each be worth 1. So y plus x are my cement walls. They're each got a cost of 1, plus the cost of the glass wall is twice the cost of the cement wall. So here's my glass wall, and it comes in at twice the expense of the cost of a cement wall. So far I've got that C, if I collect terms here, is going to be 2y's plus 3x's. And I want to write this now as a function just of x, C at x. So I want to be able to write y in terms of x, but I have this area. I know that the area is x times y, but I also know from the question that it's 3,750 square meters. So that's going to allow me to write y in terms of x. So we know that y is 3,750 divided by x. So now I can replace y with 3,750 divided by x plus 3x. And 2 times 3,750 is 7,500. And now I want my restriction, so over the interval. So this is nice because it says the glass wall, to conform to building code, the length of the glass wall must not exceed 60 meters, but not be less than 30. So that tells me that the glass wall has to be between 30 and 60 meters. So finding the interval in that case turned out to be easy. Now I want to rewrite it, C at x, so that it's ready to be have the derivative found. So I'm going to change this to 7,500 x to the negative 1. And now I'm going to find C prime at x. So that's going to give me negative 7,500 x to the negative 2 plus 3. Set it equal to 0. And this could be written like that. If I add the 7,500 over x squared to both sides, it will be positive. Multiply both sides by x squared. And I'm solving for x here. So 7,500 divided by 3 is 2,500. Square root. And I get x is positive or negative 50, but in this case, negative 50 is not within my 30 to 60 here. So I really just need to focus on x being positive 50. That's what I'm going to check, because negative 50 doesn't fit in my interval. So now I'm going to check, this is my possible peak or valley, so check peak or valley. So I'm going to substitute it in where it's easiest to, which is probably right here. So C at 50 is 7,500 over 50 plus 3 times 50. So 7,500 over 50 plus 3 times 50 is 300. Remember, these are relative. It's a relative cost. It doesn't mean it's going to cost $300 to build it. It's a relative cost, and we're looking for the minimum. And then we're going to check our endpoints. So we're going to find C at 30. Which is going to give me 7,500 divided by 30 plus 3 times 30 is 340. So far it's cheaper to go with a 50-meter glass wall. And now we'll try C at 60. Gives me 305, so it's close, but it is the minimum cost does occur when the glass wall is 50 meters. So again, we want to make sure we answer the question. So find the dimensions that will minimize the cost of construction. So we know we want our glass wall to be 50 meters, and we can get how long our cement wall is by using 3750 divided by 50. $75 meters. So now we can do a nice therefore statement. So therefore, to minimize cost of construction, the glass wall should be 50 meters long, and the other dimension, which is 2 of the cement walls, should be 75 meters. Okay, so find the dimensions that will minimize the cost of construction. We did it. We used calculus and the whole algorithm there. So another very classic type of optimization question, and similarly related to the first one, except more challenging. And now we're going to do another classic type, and that's going to be the kind of 2 types we're going to focus on and that you'll practice on as well. So this is another classic type of question here. So a cable television company is laying cable in an area with underground utilities. 2 subdivisions are located on opposite sides of Willow Creek. So here's subdivision P and subdivision Q, which is 100 meters wide, the creek. The company has to connect points P and Q with cable where Q is on the north bank 1,200 meters east of P. It costs $40 per meter to lay cable underground and $80 per meter to lay cable underwater. What is the least expensive way to lay the cable? So, I mean, they could just go straight across under the river, and then 1,200, this really should be, 1,200 should start here. Sorry about that. They could go straight across, 100 meters across, and then 1,200 meters down to Q. So that's one option. They could go straight underwater and then the rest underground, or they could go basically all underwater. Okay, so those are kind of the two extremes that could happen. But what's probably going to happen is they're going to go, so here's straight across. I'll just put that. We know that's 100 meters. So what's probably going to happen is they're going to go some distance underwater and then the rest of the distance. I'll put a little point here, maybe call that M. So they'll go from P to M underwater and then from M to Q over ground. Okay, and this, I'm going to make a right angle triangle here where this side's 100 meters. I'm going to call this distance here X. So from here to here is X, which means from M to Q is 1,200 meters minus whatever X is. Okay? And then this is a Pythagorean relationship. So the hypotenuse here, so P to M, is going to be the square root of 100 squared plus X squared. Okay, so convince yourself that that's true. If you want C squared equals A squared plus B squared, C is PM, my A is 100, and then my B is X. And then if you square root both sides, you get that side is the square root of 100 squared plus X squared. And when you get big numbers like 100 squared, I like to leave them as 100 squared as long as I can and just let my calculator deal with it later. All right, so we've got our diagram kind of drawn now. Let's start off with our word equation. So we want to minimize what is the least expensive way to lay the cable. So we want to minimize the cost. So the cost is going to be made up of the cost underwater plus the cost underground. So you see for cost underwater is so let's look back in our question here. So it costs $80 per meter to lay cable underwater. So we know it's going to cost $80 for each meter underwater, and the distance underwater we're calling P to M. And it costs $40 per meter to lay cable underground. So we know it's going to be $40 times underground, which is M to Q. That's the distance underground. So if we want cost as a function of X, it's going to be 80 times P to M in terms of X, which is the square root of 100 squared plus X squared, plus 40 times the distance from M to Q, which we've said is 1,200 minus X. And then we also want our interval. So if this little portion here is X, right there, that little portion here is X, we can see that if we went straight across, so one of our extremes was just going straight across underwater 100 meters and then 1,200 meters this way, that would mean X was 0. And then our other extreme is then we just go straight from P to Q underwater, and that would make X 1,200. So those are our two extremes. So now we have our function that we want to minimize. So first I'm going to rewrite it so it's easier to find the derivative. So C at X is 80 times 100 squared plus X squared to the half. And then I'm going to distribute here. 40 times 1,200 is 48,000 minus 40x. So now it's in a format that's more easy to find the derivative. So now we'll find c prime at x. So a half times 80 is 40 times 100 squared plus x squared to the negative 1/2, then times the inner derivative, which is 2x. And then the derivative of 48,000 is 0. Derivative of negative 40x is minus 40. So I'm going to set c prime at x equal to 0. I'm going to multiply the 40 times the 2x and get 80x times 100 squared plus x squared to the negative 1/2 minus 40. Add 40 to both sides, and then rewrite this side as 80x over the square root of 100 squared plus x squared. Okay, so I added 40 to both sides, and then I rewrote this term. So I pushed this down to the denominator, exponent became positive, and the exponent of a half means square root. So now we have this equation that we want to solve. I can multiply both sides by the square root of 100 squared plus x squared, which is going to cancel them out on this side, and I'll have 40 square root of 100 squared plus x squared equals 80x. So multiply both sides by the denominator. I could divide both sides by 40 just to make the numbers easier to work with. So 80 divided by 40 is 2x. Now to undo the square root here, I'm going to square both sides. So all the square does on this side is undo square root, so I've got 100 squared plus x squared. And on this side I have to do 2x times 2x, which is 4x squared. And then I want to solve for x, I'm going to subtract x squared on both sides. So that's 3x squared. Divide both sides by 3. Square root both sides, and again, I'm only interested in the positive square root because my interval is between 0 and 1200, so positive. So x is equal to, so the square root of 100 squared is 100 over root 3. And with these types of questions where it's a word problem, we can get an approximate value. So 100 divided by the square root of 3 is approximately 57.7 meters. So that's our point that we're going to test for peak valley. So test peak valley. So that's going to be C at, the easiest one to substitute in, probably this one here. So C at 57.7 is going to be 80 times the square root of 100 squared plus 57.7 squared. Plus 40 times 1200 minus 57.7. And keep in mind that our answer is going to be approximate because we're putting in an approximate point here, but we're comparing it to the endpoints. So let's see if we can sub that into our calculator. So when I did that, I got $54,928.20. So I just typed this into my calculator carefully, and I got $54,928.20 approximately. So now we're going to test the endpoints and see what cost we get that way. So C at 0. It's going to be 80 times the square root of 100 squared plus 0 squared. plus 40 times 1200 minus 0. So that gives us $56,000 exactly. We're looking for the least expensive way. So far, 57.7 meters for this distance here being X is working out better than this distance here being 0 and just going straight underwater and then straight underground. So now we're going to try going all the way underwater, which is C at 1200. So that part's going to be 0. So that gives you 96,000. So just going straight underwater would give you $96,332.76. Okay, so this is the cheapest or minimum cost. And then again, you have to look at what the question is actually asking. So what is the least expensive way to lay the cable? So again, we're laying the cable from P to M and M to Q. So P to M is the square root of 100 squared plus x squared, but we figured out x squared was 57.7, or x was 57.7. So that's going to give us approximately 115.5 meters underwater. So P to M, underwater. And then M to Q, that's our 1200 minus X. Is 1142.3 meters underground. So that's the least expensive way to lay the cable. So therefore, 115.5 meters of cable should be built underwater, and 1142.3 meters underground. Okay, so that's another very classic, the laying cable question is another very classic example. So the two practice questions you're going to work on one's going to be similar to the supermarket question with the one different wall, and the other one's going to be similar to this question we just did. Okay?